Good evening, everyone. Today we will start with this UV visible spectroscopy. Okay, as the name suggests, this spectroscopic technique um, it deals with the two regions, UV region and the visible region. Okay, so when you go for the UV visible spectroscopic analysis, basically we are talking about the radiations which have wavelength in the region of 200 nanometer to 800 nanometer. Okay, so if someone asks you to do a UV visible scanning of the samples, then that means that you have to do the scanning in the range of 200 nanometer to 800 nanometer, and it covers up the whole of the UV and the visible spectrum. Okay. Now, one of the important parameters over here are the radiation sources. So, when we talk about these radiations or the UV and the visible spectrum, these wavelengths, so these are basically the radiations, right? Now, when we are talking about these radiations, there must be some radiation sources which will generate the radiations within this wavelength range. Okay, so for the UV region, we basically use hydrogen lamp, which has 180, which generates radiation in the range of 180 to 350 nanometer, and we have deuterium lamp, which generates UV in the region of 160 nanometer to 400 nanometer. Okay, usually in the current day commercial this UV visible spectrophotometers, we have deuterium lamps. Okay, we have deuterium lamps. Okay, then for the visible radiations, we have tungsten filament incandescent lamp, which generates wavelengths in the region of 350 to 2500 nanometer. Okay, of the total radiation which are being generated by this tungsten filament incandescent lamp, only 15% of the radiant energy it is within the visible region. Okay, and rest of the radiations, because if you see, we talked about, when we are talking about this UV visible spectrophotometry, we are limited to 800 nanometer. Okay, so if you see, from 800 nanometer to 2500 nanometer, this radiation, these are basically a waste. Okay, and we do not use this in UV visible spectrophotometry. And as I said, of the total radiation components which are being emitted, only 15% of the radiant energy it is within the visible region, and rest of the this 85% of the radiations which are being generated by this tungsten filament incandescent lamp, they go waste. Okay, so there is a huge waste of energy, right? Then another lamp, it is there, xenon discharge lamp. Okay, now it generates radiations in the range of 185 to 2000 nanometer. Okay, so while you are using this xenon discharge lamp, we have to use a heat absorbing filter because it generates a lot of heat. So this has got some disadvantages, and due to this reason, the commercial UV visible spectrophotometer, they use two types of radiation sources. The first one is the UV radiation source, where we use deuterium lamp, which generates UV spectrum in the range of 160 nanometer to 400 nanometer, and the second one is the visible radiation, where we use tungsten filament incandescent lamp for the generation of the visible radiations. Okay. Now, apart from this, there are certain collimating system which are used to channelize the radiations through a typical path. Okay, what path I will talk about those later on. Okay, so these collimating systems, they are used to for channelizing the radiations through a specific path within the spectrophotometer. Okay, so usually the collimating systems within the spectrophotometer include lenses, mirrors, and slits. Okay, lenses, mirrors, and slits. Lenses, what do? They condense the radiations which are being generated. Mirrors, they are used to alter the path of the radiations, and slits, they only allow a specific portion of the radiations to either enter or exit a particular system within the spectrophotometer. Okay, that we will be discussing later on in the next slides basically. So what should be the property of these collimating systems? Okay, there should be some properties, and what are the properties? The properties should be these collimating systems, that means the lenses, mirrors, and the slits, they should absorb less than 0.2% of the radiations within the application wavelength range. Okay, so the absorption within a specific wavelength range should be less than 0.2%, and only then those collimating systems like the lenses, mirrors, and the slits, they can be used. Because if there is a greater absorption of the radiations by these collimating systems, so there are certain disadvantages. What are the disadvantages? The amount of the incident light which will be required for analyzing the system will be higher. Okay, so it will not be energy, what do you call, it will be consuming a lot of energy. Okay, it is not energy economical. Okay, and secondly, if something is getting absorbed within a particular system, suppose I have a matter over here and I am continuously bombarding it with a particular radiation, and this matter, it is absorbing this radiation, then what will happen? Over a period of time, the temperature of this matter will increase. Okay, so you do not want, so what will happen? Then what will happen, this, the temperature of this lenses, mirrors, and slits, they will vary. Okay, and if that happens, then these systems, they are present within the spectrophotometer. Okay, so these lenses and collimators and these mirrors, they are present within this spectrophotometer, and if they are absorbing and its temperature is going up, what will happen? The temperature within this spectrophotometer will also increase, and that is a disadvantage. So why that is a disadvantage? Because the absorption of a particular solution or a matter, it is dependent on the temperature. It is dependent on the temperature. Okay, so while using this, we have to be very carefully while selecting the material for making these collimating systems, we have to be very careful. Okay. Then we have lenses. Okay. So lenses, they are made usually with silicate glass. If you see, the working range with the silicate glass is 350 nanometer to 3000 nanometer. So you will say, sir, you said that when we are going for the UV visible spectrophotometry, we have to scan in the wavelength range of 200 nanometer to 800 nanometer. But over here, the cutoff frequency of the silicate glass is 350 nanometer. Okay. Herein, I have used a word cutoff frequency. Okay. Or cutoff wavelength, in fact, not because we are talking in terms of wavelength. So we are talking about a cutoff wavelength. So what is this cutoff wavelength? So cutoff wavelength are the limits of the optical systems within which we can use the collimating systems, including the lenses. Okay. So that means when I say that I have the silicate glasses which is having cutoff wavelengths of 350 nm and 3000 nm. That means I can only use this silicate glass within the region of this 350 nm to 3000 nm. Most of you must have attended the analog electronics class, and over there you must have studied about the band pass filter, okay, where you had a low cutoff frequency and a high cutoff frequency, and within that range you could work. Similarly, in the optical system we have this wavelength, okay, and over here these wavelengths are the low cutoff wavelength and the high cutoff wavelength, and within this what you call wavelength region you can work with the silicate glass. Okay. Apart from this silicate glass, so if you see over here, as I told you, its region is from 350 nanometer to 3000 nanometer. That means we can only work in the visible region. We can only work in the visible region if we are using the silicate glass. There are various spectrophotometers which are developed only for the visible region, and they are regarded as visible spectrophotometer. Okay. The only difference is that over there, when you talk about visible spectrophotometer, we basically work in the region of 350 nanometer to 800 nanometer. Okay, which is the visible range. Okay, which is the visible range. Okay, so in the visible, so using the visible spectrophotometer, we only work in the visible region, and using the UV visible spectrophotometer, we can work both in the UV region and the visible region. And definitely, if you are working on the visible spectrophotometer, then UV radiation, it will UV radiation sources, it will not be there over there. Okay, and if you do not want UV radiations, then you do not need the collimating systems of quartz, which are basically the crystalline silica, and fused silica, which is non-crystalline silica glass. Okay, so what is the importance of this? If you look into the this quartz and the silica glass, this fused silica systems, you can work with them from the range of 210 nanometer, and you can go up to 3200 nanometer. Okay, so you can cover most of the UV and the visible region. However, the cost of this quartz and the fused silica, that is the non-crystalline silica collimating systems, they are quite what you call costly as compared to the silicate glass system. So if you are working with the visible spectrophotometer, so if you want to design a visible spectrophotometer, you only need the silicate glass. Okay, you do not need these quartz or the fused silica systems, and also you will not need the UV radiation source over there. Apart from these differences, all the other what you call principles which governs the UV visible spectrophotometer, they remain the same. Okay. Then we have prisms. Okay. So the prisms, they are usually made up of quartz and fused silica. Okay. Now why prisms are used? Anyone? Why prisms are used?
To use a very specific, to specify the wavelengths we are using, reject the wavelengths we do not need.
Uh, Not exactly. Anyone who would like to give it a try? So it comes from your basic class 12 examples. So where you must have done some experiments with the prism. So when a light falls into the prism, it breaks down your radiation into a band of radiations. Okay, so white light, you get a band of radiations. Okay, so if we use particular what you call collimating systems or the slits, you can then get a specific wavelength. Okay, so prism, it is used to break down the white light into different wavelength components. Okay, so it is just dispersing the wavelength, so you will be getting different wavelength components at the outlet. Okay, now because of this, what happens, you can use further systems at a later stage to get those specific wavelength components. Okay, so why do you need that? Because in the spectrophotometry, what happens is that you have many wavelength radiations. Over here, if you see 200 nanometer to 800 nanometer, so it is a quite a long range. Now, when we talk about this absorption spectroscopy, in our last class, we have discussed that it is advisable that we use a monochromatic beam. What do you mean by monochromatic beam? Monochromatic beam is nothing but a radiation which is having a specific wavelength. Okay, it is having a specific wavelength. So why you want to do that? This is because if I have a molecule, say A, it may interact with the different wavelength radiations in a different manner. Okay, I gave you the example of the football field. If you are creating a wall before the goal, you will be allowing your teammate to pass through easily, and you will be restricting the other team players not to pass through the wall quite easily. The same thing happens with the molecule A also. It may allow a specific band of wavelengths, and it will interact it in a differential manner. So a molecule A, it may absorb a 285 nanometer wavelength in a greater manner, and it may allow 300 nanometer wavelength to pass through depending upon the chemistry of the molecule A. Okay, so when we are talking about this UV visible spectrophotometry, we need to understand how each of the wavelengths, they are interacting with your sample. Okay, so that is your important thing. So for breaking down the white light into different spectrums, we use prisms, okay, and they are usually made up of quartz and fused silica in UV visible spectrophotometer, okay. Then we have front surfaced mirrors. So in this front surface mirrors, the glasses, they are aluminized on the front surface. Can anyone tell me what is this? Aluminized on front surface?
A very thin film of aluminum is like deposited on the surface of the mirror instead of on the back of the surface of the mirror, so
Yeah.
that the light does not have to go through a refraction through the little like the little thickness of the whatever the substance is of the mirror.
Yeah, exactly correct. Okay. So what it does is that usually if you have a mirror, if you look our home mirror, then what happens? It is aluminized. That means a thin layer of the aluminum is put on the back surface of the glass. So initially what you have the rays which goes through the glass, it falls on the aluminum sheet and from there it gets reflected. But there are certain problems. When you are passing through the glass, as your friend told, there can be refraction. Also, when you are talking about the glass, it may absorb some energy. So some energy will also be lost. Okay, so how do you account for that loss? It will become very difficult if you are not able to account for this energy loss within the spectrophotometer reading, because it will then get added up with your sample incident radiation, because what you are doing, you are looking into the incident radiations from the radiation sources. Okay, so these are the problem, and because of this reason, the mirrors which are used for the UV visible spectrophotometer, they have these mirrors where the front surface is aluminized, so that the radiations, they come and from the surface itself they are reflected. Okay, so the mirrors in the UV spectrophotometer, they have front surface mirrors. Okay, then we have another mirrors, half silvered mirrors, and they are also called beam splitters. Okay, so what do? They are used to split the beam. Say for example, if you have this mirror, these half silvered mirrors, it will allow, if you say, if you are incidenting some radiation onto it, it will allow some radiations to pass through and it will reflect the other part of the radiation. Okay, so this type of mirrors, half silver mirrors, they are used in double beam UV visible spectrophotometers, which we will be discussing later on. Okay. Then the mirrors which are used over here, they are usually coated with magnesium fluoride. Okay, the mirrors which are used in UV visible spectrophotometer, they are coated with magnesium fluoride. Why? Because the coating with the magnesium fluoride, it reduces the scattering due to the reflections. Okay, it reduces the scattering due to the deflections. Okay, and then we have slits. So why the slits are used? As I told you previously in over here, that the slits can be used for converting a polychromatic radiation to monochromatic radiation, and they are usually used for entry slit and exit slits. Okay, and they are used basically for the entry slit and exit slit. Okay, So before proceeding further, I would like to like you to look into this color wheel chart. Okay. So can anyone tell me why I am showing you this? Anyone?
So in the absorption emission, whenever we're dealing with this, we have to look at the complementary of the color we're looking at. So, for example, like the complementary of blue is orange, for yellow is purple, and
Yeah.
for red is green. So it's like which wavelength is getting absorbed and what we are receiving. They are usually complementary while doing spectroscopic data. So I think that is why this color wheel is important.
Yeah, so exactly. So if you look over here, we have different colors. So we have red color. Opposite to it, we have a green color. Okay. Here we have blue color. Opposite to it, I am having an orange color. Okay. I have a violet color. Opposite to it, I am having a yellow color. Okay. So these are called complementary colors. Okay. So suppose if you want to pass this red color, okay, so what will happen? You have to use a green filter. Okay. So if you use a green filter, so what happens is that suppose I have a radiation source over here, then I have this green color filter, then this is optically transparent to a certain extent. Then in the output, I will be getting all the other frequency bands except the red color. Okay, because the use of this green color, which is the complementary color of the red, what it will do? It will stop the wavelengths which are corresponding to the red color. Okay, which is corresponding to the red color. Okay. So by the way, what is your name?
Saif, sir, Saif. Say
Uh-huh.
it, Saif Alam. Say it, Saif Alam, sir.
Alam. Okay. Good. So this is the reason. Okay. So we will see the example later on how this happens, and we will also see how you can develop a visible spectrophotometer in lab if you are not having access to your normal spectrophotometer or commercial spectrophotometer in the lab. Then you can definitely design your own spectrophotometer in the lab. Okay, with cheap things which are available with us. Okay. So this is an important thing. And please try to remember some of the things, especially the uh, RGB and this violet color. What are the complementary colors for these? Okay, because RGB they are the primary colors, and violet. Why I'm talking about this is because violet is the interface between the UV region and the visible region. Okay. So from the ultraviolet, we go to the violet and then we enter into the total visible spectrum. Okay. So for at least for these colors, you should know what are the complementary colors. Okay. Now monochromators. So in the monochromator, we have filters. They transmit only limited wavelength region. Okay. So if you use a red filter over here, then it will allow the wavelengths corresponding to the red color through it. Okay, if you use a blue filter, the blue light will be passed through, all other filters will be blocked. Okay, types of filter, there are different types of filter. There are glass filters, gelatin filter, and interference filter. Okay, in glass filters, what you do, we basically use colored glass and this colored glass, they usually have a bandwidth of 20 to 50 nanometer. Okay, and we use certain what you call elements or metals which are added into the glass to give color to these filters. Usually, the glass filters, they can be of research grade and normal glass colored glasses which you can find in the market. So, for designing the monochromators, we should usually use this research grade glass filters because they will be having a very narrow this bandwidth. Okay, so cobalt is used for generating blue color. Sorry, no, this should not be blue. Cobalt is somewhat reddish color. Okay, this is a mistake. Then copper, it is used for the blue green color. Manganese, it is used for the purple color. Iron is used for the green color, and cadmium is used for the yellow color. Okay. Then we have gelatin filters. So what happens is that gelatin sheets are being developed which contains organic dyes. So how these are done? Most of you must have worked with gelato. What is gelato? Gelato is nothing but gelatin, and they have been used for making some ice creams and all these things. Okay, so when you dissolve the gelatin in water at say 40 degrees centigrade, okay, they become liquid, and if you cool it down they will again become solid. Okay, now when they become liquid, if you add some dyes over here within that solution, it will give a characteristic color to the gelatin sheet. Okay, and you use this liquid for making very thin films. Okay, you can cast it onto a petri plate and then dry it, so you will be getting a thin film, and that thin film, it will be having the characteristics colors of the organic dyes, and using this way you can develop your own filters. Okay, so these gelatin sheets, they are then sandwiched between the glass filters. Okay, however, in commercial systems, they are not used much because they deteriorate with time and they get easily affected by heat and moisture, and on a long run there are bleaching of the dyes. Okay, however, it because if you want to do some research using these filters, you can do it, because the gelatin filters, if you develop it very carefully, you can generate filters using generate filters which have bandwidth in the region of 10 to 30 nanometer. Okay, however, once you have standardized your systems, it is better either to go for the glass filters or for the interference filter. Okay, now let us talk about interference filters. So I'm sure most of you would not have heard about this interference filters. Now these interference filters, they are also regarded as dichroic filters. Okay, and they also have a very narrow bandwidth, 10 to 15 nm. So if you see the glass filter, it was having a largest bandwidth. Then when you go for the gelatin filters, it was reduced, and when you go for the interference filters, it will again be reduced to a great extent. Okay, and over here the peak transmittance is for 40 to 60%. Okay, now how they are prepared? Herein optical coatings are made of different refractive indexes. Okay, and they are built upon a glass substrate. The bandwidth of the filter can be tuned by controlling the thickness and number of the optical coating layers. The main advantage of this one is these systems do not get heated much. Okay, now how does it look like? Suppose you are having a glass over here, and then over this you deposit different coatings over the glass surface. Now, from each of the surfaces, you will be having some reflections. Okay, and these reflections would be of different wavelengths. Okay, now if you use a specific slit, then you will be able to extract the monochromatic beam. Okay. Just a minute. Now, I was talking about why the prisms are used. See, the example is given over here. We have the white light, and as it is made incident onto the prism, then there is a spectral decomposition of the white light. Okay, and then we get Vibgyor, violet at the bottom and red at the top. Okay, and these are the regions. Violet, they have optical this thing in the region of 400 to 420. Then indigo 420 to 440, blue 440 to 490, green 490 to 570, yellow 570 to 585, orange 585 to 620, and red 620 to 800, 780, okay, nanometers. So these are the wavelength ranges of the different colors of the Vibgyor. Okay. Now, how to convert a polychromatic light uh, to a monochromatic light? Okay, so as there is a decomposition of the signals over here, if you see at its output, we have to apply a slit. Now, what is a slit? Slit is an opaque material. It is made up of opaque material which will block the other visible or the UV radiations. Okay, and there will be only a small opening through which the radiation will go through. Now, saying this, you have to be very careful while choosing this slit opening. Okay, so why that is so? The narrower the slit you will make, you will be getting very fine monochromatic radiations. Okay, but if you try to make it very small and the order of this diameter of the slit and the wavelength over here it matches, then there will be diffraction of that monochromatic light also, and it will not follow a straight line. So chances of that are also there. So you have to be very careful while you are choosing the width of this slit. Okay, smaller the slit you make, you will be getting towards a more refined monochromatic. But if you go below a critical level, then there will be diffraction of those rays and you will not be achieving your goal. Okay, so you have to be very careful with that. Similarly, instead of the prism, we can also use diffraction gratings. Okay, now the diffraction grating, it also uh, solves a similar purpose, and if you see white light falls onto that this grating, this staircase like gratings, and from there they can um, what you call decompose the signal of the radiations, and you apply the slit in such a fashion such that only a particular wavelength radiation they pass through the slit. Okay, there are some advantages of using the diffraction grating, and In fact, the costly spectrophotometers, they usually employ this diffraction grating in comparison to the prism. The reason being, while you are passing the white light through the prism, this is basically a matter. Okay, now this matter, this class, this should also be absorbing some of the radiations, so the radiation which are getting out, they will be having lower amount of energy. Are you getting my point? Whereas on the diffraction grating, they are mainly reflected. Okay, and due to that reflections, what you are getting, the absorption of the radiation will be lower. In other words, the monochromatic radiation which you will be getting, it will be having a higher amount of energy. Okay. Then we are getting into the this UV visible spectrophotometer, how they look like. So this one is the schematic layout of the conventional single beam spectrophotometer. Okay, so please be reminded, even though I am talking about only this UV visible spectrophotometer over here, uh, which is basically an absorption based what you call uh, spectroscopy. Any of the other absorption based spectroscopy, they have a similar arrangements. Okay, only what changes, the radiation source will change, the collimator material will changes. Okay, and the sample type they may change. Okay, so in a typical spectrophotometer, we would have a light source, we have a collimator, we have a prism or grating which will be allowing us to convert the what you call polychromatic radiations to a monochromatic radiation using a wavelength selector. Okay, so this will be a combined system changing a polychromatic radiation to a monochromatic radiation. Okay, so in this case, in the case of UV visible spectrophotometry, we have two separate things: prism or grating and the wavelength selector. Okay, in many cases it may be a single stuff. Okay, then we have sample solution, and then through which this monochromatic radiation will pass through, and this sample solution will absorb some of the radiation and it will transmit the other part, which will fall onto the detector, and this detector, it will uh, give you the readings either in absorption, how much amount of radiation has been absorbed, or in terms of percent transmittance. That means how much amount of uh, this monochromatic radiation it has been transmitted. So if you say I0, which is the incident monochromatic radiation, then how much radiation has been transmitted, if we call it as IT, how much amount of IT has been transmitted in that way also. And some amount of light will be absorbed, say IA, it can also be calculated. And if you are calculating this IA, then you are basically talking about of absorption. Okay, and if you are calculating IT, you are talking about percentage T or percentage transmittance. Okay, there is a related technique is called colorimeter, and that is called colorimetry. Okay, so what happens in this, In this, you instead of using this prism and this prism of grating and the wavelength selector combination, we use the filters like the gelatin filters. Okay, so what it does when you use a specific filter over here, so it will only allow a specific wavelength radiation to pass through. Okay, so that is also a monochromatic analysis, absorption analysis, but you can use a series of filters within that system, and just by manually changing those systems you can record the absorptions at the different wavelengths, and that system it is regarded as colorimetry. Okay, so this is the layout of a single beam spectrophotometer, and similarly, as I told you, with slight changes we can have a colorimetry system also. Then this is the schematic layout of a conventional split beam spectrophotometer. Over here, what we said, we should have a D2 lamp and a tungsten lamp. So D2 lamp, it is what you call, it is incidenting the radiation onto the mirror. Also the tungsten lamp, it is incidenting the radiations onto the mirror. So D2 lamp, it is used for UV radiations, and tungsten lamp, it is used for
Visible
visible radiations. And when it is doing this UV scanning, initially it does the UV scanning. So initially D2 lamp is on and tungsten lamp is off, and when the scanning in the D2 lamp is done, is finished, then this D2 lamp it becomes off, and the visible lamp it gets put off. Okay, and accordingly the radiation they go over here, enter into a monochromator. Within the monochromator you have the diffraction gratings. Okay, so the radiations they are being what do you call, it is being split or decomposed, and it is having an exit slit. Now through this exit slit the beam comes out, and then there is a beam splitter which we already discussed. Now through this beam splitter, the 50% of the rays they pass through the sample, and 50% of the rays they are reflected to another mirror, and this mirror it reflects that 50% of the light through the reference, and these two rays over here which is being reflected through the mirror and which is being passed through the beam splitter, so these two rays they are having identical characteristics. Okay, and through the reference it interacts with the solvent or the reference sample, and in the sample you have the sample component, and through this the radiations passes, and then you get to the photodetector. Okay, two independent photodetector, and then we do some data processing. In the data processing, what basically is done is that the radiation from the this uh, radiation from the reference, it is being the what you call, the transmitted radiation from the reference, it is from the reference ITR and say ITS. So the radiation transmitted radiation from the reference, it is being subtracted from the transmitted radiation from the sample, and then you get the wavelength. Okay, so there is a differential scanning basically. So many of you must have heard of differential amplifier. So what it does, you have a reference, you have a test amplitudes, they come over here, and at the output you get say test minus the reference, the difference between these two. So These photo detectors in the data processing, we basically what we do, we go for this differential calculations. And what are the input over here? The inputs are the outputs of these photo detectors. Okay, and then you get the wavelength spectrum. Okay, so I think our time is up for today. So tomorrow we will be continuing with the, not tomorrow, on Monday we will be continuing with this UV visible spectrophotometry. If you have any questions, I'll be happy to answer those. Do you have any questions? Any one of you?
No, sir.
Okay then.